Hello, future teachers, coming at you late on a Tuesday night. It's been a very intense day for me. But looking forward to kind of getting some stuff finalized in Kelowna. So we have a pre-recorded lesson just to finish up the integer section coming at you guys. When you view this, whenever you decide to view this, whether that be Wednesday or Thursday or Friday, you know, it's all good. It's all good in the hood to me. So we had just finished talking a little bit more about integer addition and subtraction. And what I would like to do is we're not really, I mean, we could do some multiplication if you, maybe we'll do like an example or two of multiplication. But what I really want to do is I really want to explain why a positive times a negative ends up being a negative number, and why a negative times a negative number ends up being a positive number. So that's kind of our primary goal. And then once we're happy with that, we're going to do a little bit of work with order of operations, because I think we're about ready to really start thinking about order of operations. We have our major 4 operations down, except maybe we haven't talked quite about exponentiation yet, but that'll be coming hopefully this week on Friday. But yeah, we can kind of gear up and get ready for the order of operations agreement. So let's start the lesson today by thinking a bit more about multiplication and division. So these are rules. Now, essentially, they are going to be rules that work for both multiplication and division. But we're going to work essentially just on the context of multiplication itself. So we're going to be looking at why does a positive times a negative equal a negative number, and why does a negative number times a negative number equal a positive number. There are some, I think, very accessible explanations out there on the internet, and I'm certainly not going to stop you from going and looking at some of those accessible explanations for your students. I mean, that's a great thing to do. You know, if you can explain the whole rules around multiplication and division in a couple of different ways, that's great. That's excellent, right? The more tools you have in your tool belt, the better teacher you're going to be for your students. My focus is going to be on explaining the background logic and why it makes sense for mathematicians to define things the way that they're being defined. Okay, so we're specifically going to be looking at these two options. Negative times a positive is a negative, and negative times a negative, negative times a positive is a negative, yep, and negative times a negative is a positive. Of course, since we can commute multiplication, if we multiply a positive by a negative, it's also going to equal to a negative. So we only have to really look at one case where the signs are different, and then we want to look at the case of negative times negative, because that's something new that we haven't seen yet. We know how to deal with positive times a positive. We've already talked about that in the multiplication section. So looking at these two cases, we'll cover all the 4 different cases that we could get, which would be the following, right? So we could get these 2 cases, we could get that case, and then we could get that case. So these 2 are treated in the same way because multiplication is commutative. It doesn't matter the order that my factors come in. This one we've seen already. And we're going to see that this one is similar to what we've seen already. So there's really only 2 possible cases that we get when dealing with multiplication of integers. Either we're going to deal with opposite signs, or in the long run, we're going to deal with both of these numbers being positive numbers. So let's look at case 1, which is, maybe let's work on the case of opposite signs. And kind of my goal here is to try to kind of boil this down to some logic. So what we're going to do is we're going to start with something that we know, and we're going to try to build on that to eventually show why this has to be the case. Otherwise, essentially, math is going to fall apart and bad things are going to happen, like a black hole may open up into space and suck us all in. Okay, so let's start with something we know. So, I don't know, it doesn't really matter what number we start with here. Let's start with, I don't know, let's start with the number 7. 7's a great number. We know that 7 times 0, I mean anything times 0 is equal to 0. So hopefully that's not a surprise. So essentially we want to start with something that we do know, and we know that this is for sure 100% true. There's no going back from here, right? Like this is a very obvious mathematical statement. Okay, and then this is where things get a little funky. We're going to try to rewrite the number 0 in a different way. So we know by the negative pair property that if we take a +1 and we add that to a -1, I don't really actually need to write the plus sign here, but 1 plus -1, that should be equal to 0. And that's a negative pair property concept, right? So this is one of the fundamental properties of working with integers. A positive number 1 plus a negative number 1 should be 0. In other words, a white chip added to a black chip, those things are going to cancel out, and I can remove them from the picture that I'm working with. So knowing that, we can rewrite the number 0. So we can take our 7 times 0 is equal to 0, and we can rewrite this as 1 plus -1. Okay, so we're going to take our, so the 7's going to stay there, but we're going to rewrite this 0 as 1 plus -1. Okay, and this should still be equal to 0, right? I haven't really changed the starting equation. The right-hand side should still be the number 0. Okay, so far so good. The next step is to understand that multiplication will distribute over addition, right? So inside my set of brackets, I have a 1 plus -1. This is an integer addition inside the brackets. And 7 is multiplied into this set of brackets. So 7 does distribute across addition. Okay, so next we're going to distribute that 7 across the integer addition. Okay, so what we're going to get is 7 times 1 plus 7 times -1. Okay, and this should still be equal to the number 0, right? The right-hand side hasn't changed. All I'm doing is a little bit of algebraic manipulation with the left-hand side of this equation. Okay, so we're doing pretty good. Now we would like to potentially appeal to our intuition. And we should be able to do this, I think, very easily. Okay, so let's do this. Let's say, well, I know this is a multiplication of whole numbers, and I know that 7 times 1 is equal to 7. Okay, so let's write that number 7 in here. And right now we're pretending that we don't really know what 7 times -1 is. We don't really know that. We're going to pretend we don't know that it is -7. And then the final step here is to subtract 7 from both sides. And if we do that, we're going to be left with 7 times negative 1, which remember, we're going to pretend that we don't know what that should be equal to. And if we take 0, subtract 7, we should get a negative 7 over on the right-hand side. So in other words, if I were to subtract 7 here, this would become 0. And if I were to subtract 7 here, this becomes negative 7. So effectively what I've done by subtracting 7 from both sides is I've shown that the multiplication of 7 times negative 1, which again we're pretending that we don't know, should be equal to negative 7. So we start with something that we know, which is 7 times 0 is 0. We rewrite 0 using the zero pair property, and then we can algebraically show that this multiplication of a number times negative 1 should be the opposite of what the number is. Okay, so in other words, if I start with any number and I multiply by negative 1, I should get the opposite of what I started with. And from here, you can essentially extend this out to cover all of the possible cases. So even if I wasn't necessarily multiplying, I'm going to write this just kind of in green so you can see, even if I wasn't necessarily multiplying by negative 1, like what if I was multiplying by negative 3? Well, we know that negative 3 is really 3 times negative 1. So now we can multiply the positive numbers that we know together. Oops, not 27, how about 21? And then we end up getting the same scenario that we just kind of looked at, a positive number times negative 1. So this should be negative 21. So from just proving that multiplication by negative 1 effectively gives us the opposite number, from there you have this ability to kind of decompose, multiply the positive portions together, and work out all of the other possible cases. So hopefully seeing just that kind of numerical example and the logic behind a simple numerical example, hopefully that's helpful in clarifying why that might be the case. And like I said, I'm kind of focusing on a logic and more algebraic approach, and there are other very good explanations out there as well. So with the case that we've proven, in general, we have that if we take a times negative b, this should be equal to negative a times b. So this is a generalized rule for multiplication of integers. And if you would like to see an example of how we might do something like this by hand, typically what we do is ignore the negative sign until we need to apply it at the very end. So let's say we have something like 35 times, negative 17. Now I'm curious about how I might do this by hand without using a calculator. Well, typically what I might do is just consider the multiplication of the two positive numbers, 35 times 17, and then we go ahead and we know how to multiply positive integers. We've learned that in, let's say, grade 3 or grade 4. So let's go ahead, let's multiply this out. 7 times 5 is 35, 3 times 7 is 21, plus 3 more, I believe, is 24. We'll have our placeholder 0, and then we have 3 and 5. Adding this all up, what do we get here? 5, 9, and 5. So 595. So considering just the positive numbers multiplied together, we get 595. Because we know one of our starting numbers was a negative integer, we can apply the negative sign to our final answer. Okay, so therefore 35 times negative 17 must be equal to negative 595. I apologize if you're watching this. It's late at night here. and it's wine time. So, I mean, I don't recommend having wine at 9:30 in the morning, but, maybe at 9:30 at night. Wine is okay. And as teachers, you will probably want to have a cheeky glass of wine here or there. Okay, so that is case number 1. That's dealing with a positive number times a negative number. Let's look at case number 2. Okay, case number 2 is, let me just see how I wrote this up here. Case number 2 is, we're going to show that negative times a negative should be equal to a positive, from a logical kind of standpoint. And we're going to approach this in a very similar way. We're going to start with something that we know. And we know, for example, that negative 7 times 0, this should be equal to 0. Because it doesn't matter what number I multiply 0 by, I'm going to end up with a final product of 0. So I still want this property of multiplication by 0 to be true, no matter what number set I'm working with at the elementary or high school level. So we know this is true. And we're going to use the same kind of cheeky start to this one. So we're going to rewrite 0 using the 0 pair property. In other words, we can rewrite 0 as, how do I want to do this? I want the negative one to come first. Does it matter? We'll do the positive first, just like we did in the last example. So we have a negative 7. And then inside our brackets here, we're going to rewrite 0 as 1 plus negative 1. Okay, so we're using the 0 pair property to rewrite 0 as a sum of 1 white chip and 1 black chip, for example. Okay, so this should still be a valid equation. This should still be a truthful kind of equation. And what we did last time was we distributed our number through the brackets. So we know that there's a multiplication operation here, and we're going to distribute that multiplication through the brackets. So distributing that multiplication, we're going to get negative 7 times 1 plus negative 7 times negative 1. And so the addition of these two things must be equal to 0. Now, here's where things get a little tricky. I actually technically don't know what this multiplication is. So we're kind of assuming that I don't know that a negative times a negative is a positive. That's what we're trying to algebraically prove. But I do know what this one should be equal to. I do know that when I take a positive times a negative, I get an overall negative kind of answer. So we do know this one. And that's helpful because now I can rewrite this as minus 7 or negative 7. And I still have this weird multiplication that I don't know exactly what that looks like. But this is getting us into a better scenario because now I can actually add 7 to both sides and utilize that 0 pair property one more time. So let's add 7. So you can see that adding 7 here is going to give us a 0 pair. This is 7 black chips and 7 white chips. And adding 7 over here is going to give us just positive 7, right? I have no chips and I'm going to add 7 white chips to it. Okay, so let me just kind of summarize that down here. So we're going to have negative, oops, let's do this in black just to be consistent. We're going to have negative 7 times negative 1 is equal to, drumroll, positive 7. I know it's not that exciting. You already know that that's equal to positive 7. But hopefully that gives you a little bit of algebraic background into why that's the case. And like I said, there are other kinds of explanations that might be a little bit more accessible for your students. I typically try to show it from an algebra kind of standpoint using some numerical examples, right? So there's stuff that we don't know that's inside this equation, but stuff that we do know, and trying to kind of manipulate the equation to prove something for us. So what we've done is we've proven that when we multiply two negative numbers together, our result should be a positive kind of number. So that's what we've shown here. How did I summarize that up here? So yeah, so we have shown, okay. Okay, so again, this is a really important property of multiplication by negative 1. Negative 1 effectively, multiplication by negative 1 effectively gives us the opposite of the number that we're working with. So before, when we took, let's say, positive a and multiplied by negative 1, we got negative a. It kind of flipped us over the number line. And the same thing happens down here. If I start at negative a, and I multiply by negative 1 has this effect of reflecting us over 0. It reflects us over the origin. So this multiplication by negative 1 giving us the opposite is kind of a really interesting property of integers. So in general, we have something like this. So if I try to multiply two negative numbers together, what we're going to get effectively is we're going to get negative a times b, and a multiplication. So I think about it this way. I think about this as negative a times b, and then a flip by negative 1. So that's how I'm thinking about this. Negative ab, but I flip that over the number line, and I end up with a positive kind of number overall. So there are your more generalized rules for multiplication and division. The same rules do work for division as well. So if you are looking at a division kind of thing and there's one negative and one positive, you know your overall answer should be a negative number. Or if you have two negative numbers interacting, we know that we're going to end up with a positive number. So actually, maybe I'll do a division for you here, how I might do a division question. So let's take this number. So example, let's do a negative 2,132 times, sorry, not times, let's divide it. Divide it by negative 41. So typically when I'm dividing integers, I kind of set it up the same way as multiplication. So I'm going to divide these integers without actually thinking about the negative signs until the very end. So we set this up as 2,132. We're going to divide by 41. So if I don't have access to a calculator, I'm probably going to have to use a calculator here in a second because I have a feeling I'm going to be dividing some large numbers. But this is how I would set it up. I am going to use a calculator because I don't feel like figuring out how many times 41. Oh, we could do it. It's probably like 4 times. 4 or 5. What's 41 times 5? I mean, okay, I'm the math person, right? I probably should do this not using a calculator. So how would I guess? I'm just kind of like looking at 4, and I'm looking at 213, and I'm going like 40 times 5 would be like 200. So I think like 41 times 5 is going to get us pretty close without going over. So I'm going to guess that 5 copies of 41 for 205, that's going to be as good as it's going to get at this particular step. So doing this subtraction, how many more do I need to get to 13? So I need 10, I need 5 and 3, which is 8. So subtracting, we should get 8. And we bring down our 2 for the next step, and I can easily see that 2 copies of 41 are going to go into the number 82. So we can subtract here and get a 0 remainder. So dividing 2,132 by 41 gives us the number 52. Now, some students are going to want to stop here. You just have to be mindful to go back and double check your starting numbers. So since our 2 starting numbers both had negative signs, our final answer should be positive. So what I typically, like to see is that students understand that we're dividing negative numbers, right? 2 negative numbers, but that result comes out as a positive number. So I like them to write a summary sentence like this to show that they kind of understand what's happening here, but that's a personal preference. Okay, so that should, I think, clear up all of the major operations when working with integers, except maybe working with exponents. But that's going to be some special case stuff that we talk about on Friday. So with that said, I think we're about ready to dive into our next kind of big topic inside of the integer section, which is really working with the order of operations. I like to call it the order of operations agreement, because we do have to agree on a couple of things. And let's maybe, yeah, that's fine. Let's talk about the order of operations agreement. Now, let's see. I'm curious if I can find one of these like wacky Facebook things that happens. Every once in a while you get these like weird wacky math Facebook things. So let's go math Facebook argument. And let's see if I can find one of these. Yes, like exactly what popped up over here. Exactly this. This is exactly what I want to think about. What is the answer to this? 6 divided by 2 times 1 plus 2. What is the answer to this? I wonder if I can zoom in. Anyway, let's copy this down and let's talk about why this riles so many people up. Oh, it's right here. All right, so some people get the answer of 1 and some people get the answer of 9. And we want to kind of think about why that happens and why that essentially tells us that thinking about order of operations is fundamentally important with regards to our major operations. So 6 divided by 2 bracket 1 plus 2. So example, 6 divided by 2 bracket 1 plus 2. What is this equal to? There's 2 kind of trains of thought. The first train of thought goes like this. Well, 6 divided by 2 is 3. So we get 6 divided by 2 is 3. We get 3 bracket 1 plus 2. And we know that 1 plus 2 is 3. So this is really 3 times 3. So this is really 9. Okay, so that's train of thought number 1. Do the division first, and then we kind of work through the rest of the question after we've dealt with that preliminary division. Train number 2 is where the argument starts to happen, because train number 2 is like, hey, no. Let's do what's inside the brackets first. So they're going to go, okay, well, let's do the brackets first. So 6 divided by 2, 1 plus 2 is 3. Okay, and then they tend to remember the order of operations, and the order of operations says to do multiplication and division. So what they're going to be thinking is, hey, I have to do this multiplication first. So they're going to do this multiplication and get 6 divided by 6. And then they know 6 divided by 6 is 1. So what is the actual final answer to this problem? Like, is the final answer... Because, like, we're dealing with math here, right? Like, math, as we saw in the logic section, we kind of want it to be black and white. We don't really want logic to have a gray area. So this is effectively... This is a big problem. If math had 2 different answers to a statement like this, that would be an issue. So which one's correct? In other words, I don't want to like come out and just say which one is correct. I want to put you in that uncomfortable situation where we understand as teachers that it's actually important now to think about this starting question, right? So what is it here, like what do we want to pull away from this example, right? Like, I think it's important to look at this and go, okay, this is why this is why we talk about the order of operations, because we don't want something like this to be an ambiguous thing. We want this to have a definitive kind of final answer. I think that's the key takeaway here, is the order of operations is important. We need to agree on how we proceed with things that could potentially be ambiguous. It's the same kind of thing like when we talked about sets, and we talk about like describing a set using words or describing a set using set builder notation. We want the set to be unambiguous. We want to know exactly all of the elements that are inside the set. So it's the same kind of thing here. Like, this is a thing that comes up a lot, right? Like, maybe I have to input this into a computer, and I want the computer to know how to go through, or into a calculator. Like, heaven forbid, right? What's my calculator going to say? Hopefully it says one answer and doesn't give me like, hey, it could be 1 or it could be 9. So we need to develop a way to think about these kinds of statements and agree on the order that makes sense. So this is what we mean by the order of operations agreement. So we need an agreement. So that I am not going to argue about, because there are cases when we start to put all of these operations together, right? Especially think about, what if I start throwing fractions in here? What if I start throwing negative numbers in here? It starts to get really complicated, and we need a definitive order, definitive agreement on how we want to evaluate stuff. Now, typically this is given to students in the form of like Pemdas or Bedmas, or something like this. So I've seen it as like a P or a B out front, usually followed by E. So it's usually like something like this, like Pemdas or Bedmas or something, right? So let's go with, I mean, I was taught Bedmas, but I think Pemdas is more common in the textbooks that I've seen. So let's roll with Pemdas, and I'm hoping that all of you have seen some kind of version of the order of operations so that these letters are not mysterious to you. I mean, obviously, the P stands for brackets or parentheses. E, we probably know, stands for exponents. And out of just kind of extra knowledge for you if you have to teach square roots. Square roots are a special kind of exponent. If we have some time, we will talk about this, but square roots, or really any roots like square or even cube roots, all of our roots fall into the exponent category. Okay, so if I have a square root somewhere inside of my string of things I need to do, it's as important as exponents are. Okay, next up, we have M and D, which stand for multiplication and division. Maybe I'll just write that out separately. So M is obviously multiplication. D is division. And then we have the good old last few, which are addition and subtraction. Now, what I always found helpful as a student was thinking about this in a 3-tier kind of way. So I'm going to circle the tiers that we have, and then we can kind of deconstruct these 3 tiers. So let's talk about tier number 1. So tier number 1 really deals with, I would say, the important stuff first. It says, hey, exponents are pretty important. Or, hey, if there's a bracket inside of the problem that we're working on, the brackets are there on purpose. The brackets are there to tell us that we need to work with those first. So tier number 1 always kind of wins. I always immediately start to look for, are there any brackets that I can simplify? Sometimes you can't simplify them if you have algebra expressions, but you want to look for brackets first. And if you can simplify inside the brackets, you do that first. So for those of you that may be teaching an introductory into algebra, if I have an algebraic expression like x plus 2, I'm just going to show you this. If I have an algebra expression like this and then I have like a 3, some students come here and they're like, oh, I need to add the x and the 2 together, but you don't know what x is. So I do find that in those early grades in high school, students are going to see something like this and go, oh, I have to simplify this addition first. And then they kind of mistakenly start adding x and 2 together because they think they have to simplify inside the brackets first. But the P part of our order of operations only applies if we can actually add or subtract, only if we can actually work inside of the brackets. So in this case, I'm trying to say something like, if possible. It's not always possible to work inside the parentheses, especially when we're doing stuff with algebra. So that's just one thing to keep in mind if you think you might end up teaching into that kind of upper middle school into high school. That's definitely one common misconception I see is I have to work inside the brackets first. I have to simplify x plus 2. So it is important, I think, here to say that sometimes you just might not be able to simplify inside the brackets. After I work inside the brackets and I'm able to remove the brackets, I then want to go and look at exponents. And I always call this like a tier 1 kind of thing because there's this relationship between addition and multiplication and exponents. Exponents always come first. They're the highest priority because we're going to see exponentiation is really like repeated multiplication. And we've already seen that multiplication can be thought of as repeated addition. So there's this natural tier system, exponents being the highest of the tiers because not only is it a repeated multiplication, but multiplication is a repeated addition. So addition is kind of our lowest rung of the ladder, and that's why multiplication kind of sits in the middle and why exponents always come first, because exponents are a repeated kind of multiplication. Okay, so that's a little ditty about tier number 1. So let's talk about tier number 2. I think that's not the right color, and that's going to bother me. Oh my goodness. Okay, give me a hot second here. Okay, number 2. So tier number 2 is the multiplication and division tier. To be fair, it doesn't really matter the order that you do multiplication and division, and often you're going to see that we just do multiplication and division from left to right. And I think that's kind of a bad way to think about the order of operations, because it's actually important for us to think about, how do I put this? I would say the left to right thing is less important than understanding that a number comes equipped with an operation. I think that's how I want you to think about order of operations. As soon as we get to tier 2 and tier 3, we start to think about, okay, there's certain numbers inside of this expression that come equipped with an operation. And I need to be mindful of that operation, and I don't want to incorrectly skip that operation. So I think that's how I want you to think about tier number 2. I mean, the fail-safe is to talk about left to right, but I find that a little awkward because students can sometimes lose sight of what's really important, and that is that each multiplication and each division involves like two numbers, right? There's two numbers and there's an operation that's in between those two numbers, and I need to be mindful of how those things interact. So I think it's more important to understand that a number always comes equipped with the operation that's in front of it. Okay, and multiplication and division, since they're both in the same tier, it doesn't really matter the order that we do it in. And we'll talk about what's known as the relocation property. And relocation can actually be used within tier 2, provided that I have a string of multiplications and divisions. So what I mean by like this operation, and what do I mean by this, right? So a number comes equipped with the operation that's in front of it. So let's take a look maybe at an example. So let's look at the example that we have up top. 6 divided by 2 times 1 plus 2. Okay, and let's talk about the numbers that we have and the operations that go along with the numbers. So here's our first operation, which is the division operation. The division operation has to be associated with the number 2. So 2 is associated with the division operation. So in other words, I eventually have to divide by 2. Like, that's just something that needs to be done. I need to divide by 2 eventually. There's also one other kind of key operation here inside of the tier 2. So the other kind of key operation is the multiplication, the understood multiplication between the number 2 and the number that we get from evaluating the brackets. So 1 plus 2, whatever that number is, which we know is number 3, is associated with the multiplication operation. Okay, so eventually I'm going to need to multiply something by 3, right? So that's kind of the key idea here. And often it's quite helpful to do the divisions last. That's actually my recommendation when dealing with the order of operations, is to think about doing all of the multiplications first and then dealing with all of the divisions at the end. So that's a little ditty about tier number 2. I know I'm not being super specific. The specificity, I think, is going to come out a little bit later when we actually start working on a couple of numerical examples. Okay, and then finally we have tier number 3. That's our addition and subtraction operation. They're our lowest tier because addition is the fundamental building block of multiplication, right? So it has to be tier number 3, and that's why multiplication is tier number 2. Multiplication is the fundamental building block of exponentiation, which we'll talk about. That's why exponents are tier number 1. And the same kind of thing I find happens in the tier number 3 is that we often tell students to kind of just go from left to right, but there's really nice flexibility in being able to group together nice friendly numbers. So it's just something to be mindful of. Again, sometimes we kind of fall into that trap of left to rightness. But personally, I think it's better to have flexibility, provided that you understand that a number and an operation has to go together. I can kind of move stuff around and create what we call friendly numbers. And again, it really comes down to this concept of numbers being connected together with an operation. So for example, we can take, I don't know, I have maybe a small example here. Let's go 16 plus 7 plus 14 minus 2. So I mean, I could do addition from left to right. I could do 16 plus 7, which is 23. And then I could add 14, which is 37. And then I could subtract 2, which is 35. So I could do it from left to right. And there's nothing wrong with using that as a fail-safe. But let's just dive a touch deeper into some of the properties that we know hold true for our number systems. We know that addition is commutative, right? So as long as I'm happy kind of grouping these numbers together with their operation, I can start potentially shuffling these numbers around to create numbers that add really nicely together. So for instance, maybe I want to group the 16 and the 14 together because they seem to be fairly friendly numbers, right? 16 and 14 is going to add up to give us the number 30. If I swap the order of 14 and 7, which I can do because addition is commutative, then that leaves 7 take away 2 as the other group of numbers, which again is a really nice friendly combination. This gives us the number 5, right? So this is how I tend to like thinking about addition and subtraction, and we'll talk about more examples of multiplication and division, is I can kind of use this idea that multiplication and addition are commutative to kind of group together really nice groupings of numbers. And if I don't have access to a calculator, which, to be frank, I mean, most students don't need a calculator until they hit high school anyway. Wow. I think they should work on their fundamental mental arithmetic. I think having this flexibility of commutativity to be able to move stuff around is really, really helpful. So we often call this, I've heard it called the relocation property. And the idea is we can use the commutativity of addition and multiplication to kind of swap the order of certain numbers to make things a little bit friendlier to work with. So yeah, we do have an overall kind of tier system when it comes to the order of operations agreement. I always want to kind of first and foremost think about brackets and exponents. Then I want to kind of look at what things are multiplied and divided. And then finally, I want to look at what things are added and subtracted. But along the way, as soon as I hit tier 2 and as soon as I hit tier 3, I can start thinking about, is it possible to use commutativity to make some of these computations a little bit easier for us mentally? Okay, so the idea here is to use our mental math skills and be able to use that commutativity, the commutativity property to kind of make some of these computations a little bit easier for us to handle. So let's take a look at a couple examples, and that should, I think, finish up our lesson today. So let's look at a nice string of multiplication and division. So let's say I want to give this to my students, 33 times 13 divided by 2 divided by 11 divided by 13 times 10. Okay, so take a moment to think about how we might try to group some of these things together to make them a little bit friendlier to work with. Now I'm going to come through and I'm going to start thinking, I'm going to start processing the order of operations in that tier kind of way. So I look at this big expression I have and I go, do I have any tier 1 stuff to worry about? Well, no, I don't have any parentheses or brackets. I don't have any exponents. So I move into tier 2. Do I have any multiplications and divisions? Yes, this whole question is only multiplication and division. So I only have tier 2 kinds of things. So what do I know about tier 2 kinds of things? Well, I can commute via multiplication. So looking at some of the stuff that we have, let's take a look at, for example, number 33. Are there any other numbers with their associated operation that we can commute to maybe put beside 33 to make it, I don't know, a bit more friendly? Well, I don't really want to multiply by 13. I could do it using the algorithm, but that's not a friendly mental math kind of question. Is 33 divisible by 2? Well, it's not divisible by 2 because it's not even, so I don't really want to group it with a division by 2. What about a division by 11? Oh, okay. So 33 is divisible evenly by the number 11. So it kind of makes sense for us to relocate that division by 11. We're going to group that division by 11 with the number 33. Okay, so next up we have a multiplication by 13. So I'm going to write down multiplication by 13. And then I'm going to start scanning what I have left over and see what might be helpful to regroup with this number 13. Is writing down the division by 2 next going to be a helpful thing? Probably not, because 13 is not an even number. But I do have this division by the number 13. Actually, I need to change that to blue here. That might be a helpful thing to write down next. Okay, so as long as I move the number with its associated operation, I can do that. That's totally fine. This is using the commutativity property of multiplication. Even though there's a division sign here. Because we'll talk about it a little bit more with integers, but division is kind of like multiplying by a fraction. So as long as you're mindful of keeping the number with its associated operation, you can move that number with its associated operation, which is kind of cool. Okay, last but not least, we have two more numbers that we want to work with. It looks like 10 and 2. These are going to be nice, friendly numbers to work with. I always do the multiplication first, followed by the division. This should be a division by 2. Okay, so that's how I would write out this relocation or this commutation of these 6 numbers. And once I kind of relocate and make these numbers into friendly pairs, I can go through and I can mentally evaluate all of these things. 33 divided by 11, well, that's 3. Okay, I'm going to bring down my multiplication sign. 13 divided by 13, well, that's 1. Bring down my multiplication sign. 10 divided by 2, that's 5. I know that anything times 1 is itself, so this is really like 3 times 5, which is equal to 15, right? So just having a little bit of flexibility in where I place these numbers is very helpful from a mental math kind of standpoint, right? It allows us to kind of group things together and not have to rely on doing an algorithm or not have to rely on using a calculator to get some of this work done. Okay, let's do one more example for today, and then I'll show you, I've posted up a practice worksheet for you so you can kind of work away at that. And then I think when we get back together next week, we might do 1 or 2 of those questions together so that you have a chance to practice, but we also have a chance to kind of chat a little bit more about some of those harder questions. Okay, so we have negative 22 plus negative 37. And then we're going to have a little string here of multiplication and division. So plus 55 times 3 times 72 divided by 11 divided by 12. Okay, plus negative 3 minus negative 2. Okay, so our goal is to well, one, we want to use the order of operations agreement. So we want to go through our 3 tiers and kind of work on each tier one by one. And being mindful that as we're inside of tier 2 or inside of tier 3, it's possible to use commutativity to relocate some of these values. So let's look at tier 1 first. So working with brackets, working with exponents. There are no exponents, there are no square roots, so there's nothing I have to worry about there. We do have a couple brackets. So what I typically recommend to students is we want to use some of the things that we saw in class just to kind of simplify some of these operations first. I do want to get rid of the brackets with my integers here. So let's just go through in green. And I know that adding a negative number is really like subtraction. Adding a negative number is like subtraction. And subtracting a negative number is really like addition. So that's the first thing I'm going to do, is just try to simplify this a little bit so that I don't have those brackets around my integers. I'm going to keep everything else the same. I'm just simplifying some of these expressions first. So there we go. There's a simplified version that doesn't have any brackets. Okay, the next thing I typically try to look for is, now we're going to move into tier 2, and tier 2 says identify all of your multiplications and divisions. So here are all of the numbers that are connected together by multiplication or divisions. I want to work with this grouping of numbers first. So I'm just going to copy these numbers down. So let's copy down 55. It's a positive kind of 55 times 3 times 72 divided by 11 divided by 12. So I'm just going to copy these numbers down. I'm going to work inside here because I want to do all of this stuff first. But we want to check to see, is it possible to do any of this stuff in a nice way? So can I group, for example, can I group 55 with something else in here to make a friendly combination? Well, I mean, we could probably multiply by 3. I definitely don't want to multiply by 72. Oh, 55 is divisible by 11, so maybe it makes sense to couple those things together. Okay, we have a multiplication by 3, but I mean, dividing 3 by 12 is going to give us a decimal number, so that's not helpful. So 3 probably is not going to get grouped with anything else. And that leaves us with 72 getting grouped with a division by 12, and that should be okay. So now let's go through and do this mentally. 55 divided by 11 is 5. We have a multiplication by 3. And then we have 72 divided by 12. Is that 6? I think that's 6, right? Okay, I'm going to use commutativity here because I don't want to do 15 times 6. I can't actually remember what that is, but if I do 5 times 6, I know that's 30. And then I know 30 times 3 is going to be 90. Okay, so again, I'm just using the commutativity to move the 3 and the 6. I'm just being mindful that I'm going to take the, I'm essentially moving all of, I have it, not have that in black, I want that in green. I'm moving all of this over to here, right? And I'm moving all of this over to here. So I'm taking the number as well as its associated operation. And that just makes the multiplication a little bit easier from my mental standpoint. Okay, so let's go back and kind of see what we have left over up top. We haven't really dealt with the negative 22 minus 37 yet. Then we're going to have a plus 90 that we just evaluated. And then over here at the end, we have a minus 3 plus 2. So this is what we've kind of boiled this down to. Now we're inside of tier 3. And again, I can kind of move these numbers around a little bit if I need to potentially make them nice to work with. Now, I do notice here that I have a couple numbers that end in 2. That might be helpful. I've also noticed that because this number ends in a 7, and if I do 90 take away 3, that's going to give me also a number that ends in 7. Those could be potentially good numbers to group together. So let's go ahead and use the commutativity of addition. We're going to get the negative 22 grouped together with the addition of 2. Let's do the plus, maybe the plus 90 minus 3 next. And then we'll move the negative 37 to the end, and we'll deal with that at the very end. So negative 22 plus 2 is negative 20. We have 90 minus 3, which is 87. And then we can see that that's going to nicely kind of connect together with our subtraction of 37. So we have negative 20 plus 87 minus 37, I think is going to give us 50. I like to kind of commute this and make this look like 50 take away 20 in my brain. And that way I know that my final answer here is going to be 30. So that kind of guides you guys through a couple of different examples here. And hopefully those examples have made sense. I would say online, so if you go into our Moodle, am I on the dashboard here? Yes, hopefully I'm still logged in. If you go into Moodle, I have uploaded a practice worksheet. So I would say, just take a few moments. So under the working with integers, there's an order of operations worksheet called intense version, because it's pretty intense. This is a worksheet that one of my friends uses to give to her advanced grade 4 class or grade 5 class, and maybe like try to work on the first couple, right? So maybe work on 1 and 2, try to get some answers for maybe 1 and 2 before Monday, and then on Monday we'll do a little bit of review of order of operations and try to simplify 1 and 2 together. Okay, so maybe that's my recommendation for homework. Try a couple of these, see if you can kind of get things to work out, and then we will we'll review some of that next week. So let's finish off class by looking at this one more time. So what is the answer? Is the answer 1 or is the answer 9? Well, knowing our 3-tier system, I do have to simplify the brackets first. So that gives us 6 divided by 3 with the 3 in the brackets. And if we interpret this as a multiplication, then we can rewrite it in the following way. We have 6 divided by 3 times 3. Now, where people run into issue is actually right here. What they sometimes want to do is maybe multiply this first. But I think it's in a pretty nice order already, right? I think that 6 divided by 3, that's a thing that we can actually evaluate. So 6 divided by 3 is 2. What? Did I do something wrong? That's crazy. This is weird. So I guess is our final answer 6? Is it 1 or not? What? Why did I get 6? That's crazy. That's crazy talk. What did I do up here? Did I write something down wrong? Oh, 6 divided by 2, 1 plus 2 is what it is. So 6 divided by 2, 1 plus... I just wrote it down wrong. That's my bad. Okay, so this should really be a 2. 6 divided by 2 is 3. So actually our final answer here should be the number 9. So according to what we believe to be the order of operations agreement and thinking about numbers going together with their associated operations, the final answer here should be 9. So what's the flaw in thinking for the number 1? Well, typically the flaw in thinking... how did we get the number 1 again? The flaw in thinking is this. Most people are happy doing the work inside of the brackets first. And then the flaw that happens is they want to multiply these two numbers to get this. And that's incorrect. And that's incorrect because 2 has the division operation associated with it. So we can't do 2 times 3 because we're skipping over, we're glossing over the fact that we should actually be dividing something by 2 rather than multiplying something by 2. So that's where the flaw lands. So 1 is not correct because we're not honoring this idea that 2 has to be associated with a division kind of thing and not a multiplication kind of thing. So there you go. Hopefully that kind of ties everything nicely together. And that is your class for this lovely Wednesday or whenever you might watch it. And we will chat a little bit more. Let's see, we've done integer stuff, which I'm happy with. So we'll probably do a little kind of recap of working with exponents on for Friday's class. All right. So that is everything for today. Have a lovely Wednesday and a lovely weekend, a lovely Friday. And I will see you all next week.